Name of Almighty Allah, the most gracious, the most merciful. As Muhammad, peace be upon him, narrated, if anyone travels on a road in search of knowledge, Almighty Allah will cause him to travel on one of the roads of paradise. Hello everyone, this is Dr. Tariq Masood. Thank you very much for watching my videos and your wonderful support to make this channel a grand success. We are a family, a partner. Please share and subscribe our channel if you haven't done so far. We as a team can work together to convert challenges into opportunities and opportunities into success stories. These success stories can be monetized into value addition in the world by large. Thank you very much for your precious time. Today I'm going to discuss my lecture number 4 on fluid catalytic cracking, startup, procedures. Before my lecture, I used to read a Quranic verse called Rabbi Shrah li Sadri wa Yassir li Amri wahlul uqdatam min lisani yafqahu qawli Allahumma Rabbi Zidnillah. O my Lord, open my chest and ease my task for me, and loose a knot from my tongue that they may understand my saying. Allahumma Rabbi Zidni ilma. O Allah, advance me in my knowledge and true understanding. Okay. Fluid catalytic cracking, FCC unit, lecture number 4, normal operation and startup procedure. Okay, key takeaway points from lecture number 4. We have already discussed process control guidelines, reactor and regenerator heat balance. We are still discussing. On later stage, we will discuss conversion, gasoline selectivity, C3 and C4 recovery, off-specs handling, slope handling, set point list for main process control mechanism. Okay, regenerator heat balance. This is on 1 kg of coke. Heat consumed to heat up the regeneration air. Since delta H is equal to mass times by Cp times by delta T, the air is heated from the main air blower discharge temperatures of 204 degrees Celsius to the average hottest temperature of 746 degrees Celsius at an average specific heat of 0.26 kilocalorie per kg degree centigrade. Okay, delta H air is equal to 170,492 kg per hour, which we have discussed earlier. Air divided by 11,424 kg per hour coke times by 746 minus 204 degrees Celsius times by 0.26, that is the average specific heat, kilocalorie per kg degree Celsius equal to 2103 kilocalorie per heat coke being produced. Okay. Next is the heat consumed to heat up the regeneration air water vapor. Okay. Water vapor is heated from 204 to 746 degrees Celsius at an average specific heat of 0.5 kilocalorie per kg degree Celsius. Okay, heat consumed to heat up the regeneration air water vapors. Water vapor is heated from 204 degrees Celsius to 746 degrees Celsius at an average specific heat 0.5 kilocalorie per kg degree Celsius. Delta H water is equal to 1964 kg per hour water divided by 11,424 kg per hour coke times by final temperature, that is 746 minus 204 C times by specific heat, that is 0.5 kilocalorie per kg. So it's equal to 46 kilocalorie per kg coke. So the heat consumed to heat up the regeneration air water vapor is 46 kilocalorie per kg coke. Okay, next topic here. Okay, heat consumed to heat up the coke. Coke is heated from the reactor temperature of 521 degrees C to average hottest temperatures 746 at an average specific heat of 0.4 kilocalorie per kg degree Celsius. Delta H coke is equal to 746 minus 521 degrees Celsius times by a specific heat, that is 0.4 kilocalorie per kg is equal to 90 kilocalorie per kg coke. So the heat consumed to heat up the coke is 90 kilocalorie per kg. Okay, heat consumed to generate steam in the catalyst coke. Enthalpies of water and steams are obtained from steam tables. Number one, water in at 104 degrees Celsius is equal to 105 kilocalorie per kg times by 25,416 plus 3,153 kg per hour is equal to 3 times 10 to 10 to power 6 kilocalorie per hour. Number two, steam out at 239 degrees Celsius is equal to 670 kilocalorie per kg times by 25,416 kg per hour is equal to 17.03 times by 10 to power 6 kilocalorie per hour. Number three, blow down out at 239 degrees Celsius is equal to 245 kilocalorie per kg times by 3,153 kg per hour is equal to 0.77 times by 10 to power 6 kg per hour. Okay, catalyst cooler duty is equal to 17.03 plus 0.77 minus 3 times to 10 to power 6 kilocalorie is equal to 14.8 times by 10 to power 6 kilocalorie per hour. Or we can also write in the other form, delta H removed is equal to 14.8 times by 10 to power 6 kilocalorie per hour divided by 11,424 kilocalorie per coke is equal to 1,295 kilocalorie per kg coke. Okay, next is a regenerator heat balance. Regenerator heat balance. Using a typical regenerator heat loss rate of 139 kilocalorie per kg coke, the heat consumed to heat up the catalyst is first, regenerator heat. Delta H combustion coke minus delta H coke minus delta H air minus delta H water vapors minus delta H loss minus delta H removed. Second is heat regenerator. 9,558 minus 2,103 minus 47 minus 90 minus 1,295 minus 139 is equal to 5,884 kilocalorie per kg coke. Okay, next calculate the catalyst circulation rate or CCR. Okay, calculate the catalyst circulation rate. The catalyst is heated from the reactor temperature of 521 degrees Celsius to the regenerated catalyst temperature of 744 degrees C. An average specific heat of 0.275 kilocalorie per kg degree Celsius. Since Q is m Cp delta T, then m is equal to Q over Cp delta T. So the CCR, catalyst circulation rate, is equal to coke kg per hour times by regenerator heat kilocalorie per kg coke divided by specific heat, average specific heat times by catalyst temperatures minus regenerator temperatures. The CCR is equal to 11,424 kg per hour coke times by 5,088 kilocalorie per kg coke divided by 0.275 kilocalorie per kg, that is average specific heat, times by 744, that is regenerated catalyst temperatures, 740 minus 521, that is reactor temperatures, times by 60 minutes per hour is equal to 18,268 kg per minute circulation. Or in the other way, that CCR is equal to 18,268 kg per minute per 1000 kg is equal to 1 ton is equal to 18.3 ton per minute. The catalyst will be circulated. Okay. Next topic, calculate the catalyst and oil ratio. Okay. Calculate the catalyst oil ratio. Catalyst oil ratio is equal to CCR, catalyst circulation rate kg per hour divided by fresh feed kg per hour. So the catalyst oil ratio is equal to 18,268 kg per minute catalyst times by 60 minute per hour divided by 187 to 99 kg per hour of fresh feed is equal to 5.85, that is catalyst to oil ratio. Okay, next topic here. Okay, calculate the regenerator efficiency. Regenerator efficiency is equal to regenerator heat times by 100 divided by delta H combustions of coke, which is equal to, if we have 5,1884 kilocalorie per kg of coke times by 100 divided by 9,558 kilocalorie per kg of coke, that is as we have given in the first formula. So that equal to 62%. This number will be higher without catalyst cooler. Next is to calculate the delta coke weight percent. Delta coke is equal to coke kg per hour times by 100 divided by catalyst circulation kg per hour is equal to 11,424 times by 100 divided by 18,268 times by 60 is equal to 1.04 weight percent of catalyst delta coke. Okay, conclusion. What we discussed today? Regenerator heat balance conversions, heat consumption to heat up the regeneration air, water vapors, heat consumed to generate steam in the catalyst cooler, heat consumed to heat up coke, calculate the catalyst circulation rate, calculate the catalyst oil ratio, calculate the regenerator efficiency, calculate the delta coke weight percent. Okay, we are still discussing heat balance reactor heat calculation. My next topic will be conversion. These are a few references. Together, everyone achieve more. Please do not hesitate sending your feedback, comments, t.masood.dr@path.edu. Thank you very much for your precious time. Please stay safe, stay inspired and blessed. Thank you very much. God bless you all.